All right. All right, so today's lecture is a continuation of last week's lecture on Module 1, Crystal Structures and Electronic Materials. And the main topics, just as a quick review of what we talked about last time and the importance of this module. This module talks about how atoms are arranged in solid materials, some of these semiconductor materials that we are going to be talking about. And remember, like one of the key concepts is that atomic structure determines the properties of a material. Whether you're talking about the mechanical domain, the chemical domain, the thermal domain, or electrical domain, the atomic structure determines the properties of a material. So in this module, we are talking a little bit about different types of atomic structures. So we're talking about three-dimensional crystals, and we're talking about two-dimensional crystals. We'll be talking a little bit about that in class today. As a quick review of last time, what is the three-dimensional crystal structure of a silicon lattice? What is that crystal called, the unit cell called?
Is it a diamond cubic?
Close, very close. Anyone else want to take a guess? It is diamond. It has the word diamond in it.
Diamond lattice?
Yeah, it's just called the diamond lattice. That's right. Now, it does have a cube form, so I understand where the cube came from, but it's just called the diamond lattice. And so how many atoms? Each silicon atom is bound to how many atoms around it?
4.
4. That's correct. Each silicon atom is bound to 4 silicon atoms around it. This is because silicon is column 4 in the periodic table, so it has 4 electrons in its outer shell. What type of bond does silicon form with its neighboring silicon atoms? There's different types of chemical bonds. Really, we only talked about one type of chemical bond in this class. So I just want to see if you, what was it? Covalent bonds. Right. That's correct. And what defines a covalent bond?
It's sharing an electron with the adjacent atom.
Exactly. Right. So this key point here from last time in class, you have a silicon atom and then you have a bunch of, one covalent bond is where a silicon atom shares an electron with its neighboring silicon atom. Okay, and if you imagine that this repeats, so you have a total of 4 silicon atoms around it, so it forms 4 covalent bonds, and therefore it creates a lattice structure with 4 neighboring atoms. Now, the principle is that an atom is in a stable state when it has 8 electrons in its outer shell. So, you count up the number of atoms that you have here. Each of these covalent bonds provides 2 electrons. Okay, and the way we think about it is that the central silicon atom provides one of the electrons, and the bonding silicon atom that's bound to it provides the second one. So these then have a total of 8 electrons in the outer shell for this central silicon atom. Okay, and these are called hybrid orbitals. We'll talk about orbitals in the next module. Okay, so we said that like in 3 dimensions, when we draw this on paper, we draw it in 2 dimensions. We just draw this stick model, silicon with like 4 sticks around it. Each stick is a covalent bond that contains 2 electrons, but in actual 3-dimensional space, you form what looks like a tripod. This is called a tetrahedral bond. And does anyone know why it forms this type of 3-dimensional structure? Why doesn't it just look like this, like in plane?
Because the atoms are trying to be equidistant apart.
That's right. They're trying to be as far apart from each other as possible. And if we're really stickler about it, we can say that the electrons are the ones that are trying to be as far apart as possible from each other, because electrons repel each other. So these sticks, yeah, if you look at these 4 sticks in a 2-dimensional plane, they're not as far as they could be, If you in 3 dimensions, if you spread them out as much as possible, you'll find that they form a 109.5 degree angle, and that's the tetrahedral bond. Okay, so we talked about the silicon diamond lattice. We talked about how there's like 8 corner atoms. There's 1 atom on each one of the faces, each one of the 6 faces, and then on the interior, there's 4 additional interior atoms. Okay, so we calculated the volume density of the silicon diamond lattice. And then we talked about Miller indices. So you'll have some example problems on Miller indices today, and that will be assigned in the homeworks. And we talked about the different families of planes at the end. So I'll just touch on that real quick. The different families of planes, if we just want to think about it in terms of what are the key points to remember. In any type of lattice, there's often symmetry. So if you look at the distribution of atoms, if we go back to the diamond lattice here, if you look at the distribution of atoms on the top face, there's a certain density of atoms. There's 4 on the corners and then 1 in the middle of the face. And if you compare that to the bottom face of the cube, this also has 5 atoms with 1 in the middle. So there's symmetry. In fact, any face of this cube is going to have the same distribution of atoms on it. So because of that symmetry that exists in the crystal, we talk about this concept of families of planes. So we're basically saying that this top face, the bottom face, and as it turns out, like any of the 6 faces of this cube are all part of the same family of planes. The family of planes means that regardless of which plane you choose within that family, the atomic distribution is going to be the same. Okay, and just to be a little bit more specific about this, I'm going to, let's see, I'm going to open up my OneNote here. All right. Okay, let me know if everyone can see my notes here. You just put a thumbs up there if you're able to see it. It should be blank, by the way. Okay, good. So if we look at one of the faces of the atom, we will find that if we look at one of the faces of that cube, there's these 4 corner atoms, and then there's 1 atom in the middle. So this is what it looks like. So I'm just going to draw the 3-dimensional cube here. Okay, and I'm just going to call this bottom plane. We're going to call this plane 1. Okay, and this side plane, we're going to call this plane 2. Okay, if we look at the atomic distribution on plane 1, it looks like this. If we look at the atomic distribution on plane 2, it also looks identical. Okay, by the way, just a reminder, we are drawing the atoms on the faces of the diamond lattice. Okay, so whether we're looking at the bottom or the side, doesn't matter. So what we say is that this bottom face and all the side faces and the top face are all part of what's called the 100 family of planes. Okay, and this 100 family of planes includes the 100 plane, the -100 plane, the 010 plane, the 0-10 plane, all these different planes, 6 different planes. They have different Miller indices, as you can see here. We talked about Miller indices last time, and they're all basically equivalent to one another. So a plane in the 100 family of planes is something that's on the face of the cube. Now, the next family of planes, which is part of the 110 family of planes, the one I'm circling right now. The 110 family of planes is any plane is constructed by cutting across the cube. Specifically, you take one face, you draw a diagonal across there. You go to the opposite face. So we started at the top, we drew a diagonal. Then we go to the bottom and we draw a diagonal. And then we connect those two lines together with the plane. Okay, that's how you get a plane in the 110 family of planes. Okay, so the 100 family of planes cuts across the cube. Okay, but it is also coincident with two of the edges of the cube. So it cuts across two faces of the cube, and then it's coincident with two edges of the cube. The 111 family of planes. Now this family is constructed by taking, cutting across, drawing diagonals across three adjacent faces. So let's say we start off with three adjacent faces, start with the bottom one. The side face is next to that. This side face is next to that. Now on each one of the three faces, we draw a diagonal across there. Okay, and then we connect those three diagonals with the plane. So you can see it kind of looks like a triangle here. So the 111 family of planes kind of cuts through, it also cuts through the cube like the 110 plane, like the green one here, but it does so in a different way. You can see that the plane has a slightly different angle. Okay, and one of your homework problems is to actually look at the atomic distribution on the 111 family of planes. So I want you to kind of think about that as a mind bender here. I'll just get you started on it. The 111 family of planes, so if you say 111 family of planes, the way that we're going to draw that is it's actually going to look like a triangle. Okay. So it's this red triangle here, and I just drew that triangle separately. So this cuts across one of the faces of the cube. This cuts across another face of the cube, and then this cuts across a third face of the cube. So from here, you can kind of figure out like if there are going to be atoms at the vertices, if there are going to be atoms perhaps in the middle here, and if there's even one inside the triangle. That's all some things you have to think about. Okay. So that's one of the homework problems. So I'm not going to go into the details there. But if you try the homework problems and you're struggling with it, you know, come ask me questions and we'll go over this again. All right, so any questions on the planes, the review of the planes? No questions yet? Okay. How about this, just to make sure that everyone's following here. We did this in class last time, but we can do this again real quickly. So what is the area density? The area density in the 100 family of planes. So this is, again, I'm putting here 100 planes. Question from Melvin. Would it be accurate to say that the 100 family of planes includes all the faces of the cube? Yes, that is absolutely right. Any face of the cube would be considered part of the 100 family of planes. Thanks for that question. All right, so when we're calculating area density, let's just walk through this real quick as a review from last class. So how are we going to do this? What's the first step?
Just the number of atoms on the face over the area of the face, right?
Correct. Good. First step. So number of atoms in, I'm just underlining this because it's the number of atoms in the unit cell divided by the area of the unit cell. Okay. And when we consider the number of atoms in the unit cell, we just have to remember this, is that we're just going to draw the atoms as circles now. How much of a corner atom is contained inside the unit cell?
Quarter.
Quarter of it.
1/4 of it. Yeah, that's right. So just highlight this here. We're just shading this in. 1/4 of that circle is inside the square. All right. And then there's also a center atom here. So let's start with the corner ones, right? So there's 4 corner atoms, and since each corner atom is only 1/4 inside the square, we multiply that by 1/4. And then we also have the center atom. What do we multiply the center atom by?
Hello.
What was that, Janan?
Is it the center atom? Is it on the surface? Sorry. Is it on the face of the cube, or it's like the inside?
Oh yeah, this center atom. If we look at the faces of, if we look at a silicon lattice, there's actually one atom on the center of each face of the cube.
Would you have?
I couldn't quite hear you, Janan.
Would it be 1/2?
No, it won't be 1/2. So this is kind of actually a bit of a trick question. The key thing is this whole thing, the whole circle is inside the the whole thing is inside the unit cell. Right? You see how the corner atoms, only 1/4 of them were inside the unit cell, but for the center one, the entire thing's inside the unit cell. So it's just going to be multiplied by 1. All right. So that is our that is the numerator, the number of atoms in the unit cell, and then the area of the unit cell is just make this a little bit bigger. The area of the unit cell, we know that the length here is A. We know the length here is A. And so the volume here is going to be A squared. Okay. Excuse me for 1 second here. Sorry about that. I had an open window. It started raining. Okay, so the number of atoms in the unit cell is going to be equal to 4 times 1/4. So that's 1 plus 1. So that's 2 divided by A squared. Okay, and we're just leaving it in variable form right now. But this is how you'd find the area density here. So you're going to be asked to find the area density of some of these things on the 1, 1, 1 planes. So think about that. Think about which atoms reside on, on the outside or inside. But this requires more thinking, okay? All right, so let's continue now. We are now going to talk a little bit about the manufacturing of these of the silicon of these single crystal silicon chips. So how do we actually make this diamond lattice? We have this structure here that we said silicon bonds to 4 other atoms around it, and then in 3 dimensions they form this type of nice repeating crystalline structure That's a silicon lattice. And just as another point from last time, this was a TEM image of crystalline silicon, where each atom is nicely bonded to 4 other atoms around it, and is very repeatable and beautiful crystal lattice. So one of the key things in industry, that the reason why semiconductors have become so prevalent in our everyday life and why they're so reliable, is because our manufacturing capabilities have really like risen to a scale where we can make these things with atomic level precision, I guess you could say. It's not to say that we put atoms together 1 atom at a time. No, but it is to say that we can make these things in a reliable way so that you can form these very repeatable crystal lattice structures. All right, so the way that it begins is that there's a little video here that we can watch, but I just want to walk you through this first. The forming silicon microprocessor. Eventually, this is what this is going to look like. It's an Intel microprocessor, for example. It actually starts with sand. Silicon comes from silica. Okay, don't mix those two up. Actually, it's one of the most common mix-ups is the following. Let me just write it down on this slide. There's silica. There's silicon. And then there's silicone. Okay, just so we're clear on this, silica is basically sand. All right, that's this. It turns out this is like the 2nd most abundant element on Earth. All right, so we're fortunate that a lot of our semiconductors are made from a very vastly available material. All right, so silicon is this thing here. This is also silicon. Okay, when you take silica, it goes through a process called the Czochralski process, which removes some atoms from the silica and makes pure silicon. Okay, silica has silicon plus some other stuff in there. Okay, so think about it that way. And that is basically sand. We go through this process called the Czochralski process, where this stuff is melted down. You'll see a video on that, and it forms something called a silicon ingot. An ingot is a tall cylinder. We'll talk about that more. That is eventually cut up into thin slices like this. All right, these are called silicon wafers. Silicon wafers. This is a silicon ingot. So if you imagine taking this thing and slicing it down with a saw into really, really thin wafers or slices, we call the wafers slices, or we call it slices wafers. Sorry, it's the other way around. And then we polish them into something that's atomically flat so that we get very, very nice atomic scale properties, atomic scale reproducible properties there. Okay, and when you look at these things, they'll have a mirror finish. You could see your reflection in them. They're so well polished. Okay, they're typically about 500 microns, 0.5 millimeter thick. Now from here to here, this is where the value of this increases. So just to give you a sense, one of these wafers, when it's first made like this, an empty wafer, might have a value on the order of, let's say, $20. Okay, maybe 20 up to $100, let's say. The value of this thing here after the next set of steps is, it can be a million or more. So going from here to here, this is called semiconductor manufacturing. So this is what a foundry does. A semiconductor foundry goes through these manufacturing steps, and most of the chips nowadays do a process called CMOS fabrication. All right, and that a CMOS fabrication actually consists of not just one step. It's like several hundred steps that are done inside a clean room. A clean room is one of those, those bright white rooms that you see that have, we showed some videos of that in the first class where people are wearing those bunny suits and there's very, very few dust particles in the room. And so those processes are done by humans, by robots inside these very, very clean facilities. And there are processes that are called like lithography, where the transistors are patterned. There are processes called like metal deposition steps, where very, very thin films of metals are deposited to make interconnections between the transistors. And then the transistors themselves. The transistors themselves are made using processes where the silicon wafers are put into furnaces and you flow like a process gas through there that forms P regions and N regions. There are processes that are used to form the gate oxides that are a critical part of transistors. So basically a whole bunch of different manufacturing processes that are done under super well-controlled conditions. And I'll just mention this again, like this could be, the value of this could be greater or even much greater than $1 million. Okay, where the value of this might be less than 100 or so, each wafer I'm talking about. The reason why this has such a high value is because one of these wafers, just one of these wafers could have hundreds of microprocessors on it. Okay, so when you see this, this is the microprocessor, and if you've ever built a computer yourself, you may have seen that this is the key part of the computer, and this sits on something called a motherboard. And the motherboard allows this central microprocessor to be connected to everything else, like the video cards, the USB, the USB ports, the hard drive, the memory, right? But they're all connected to this microprocessor. Okay, this is the brains of the computer. But one of these wafers, after they are fabricated, like I said, could contain hundreds of microprocessors that are laid out here. And you basically cut these, you cut vertically and then you cut horizontally. So you cut it into little squares, and each one of those little squares, if you can kind of look here, each one of the little squares is actually a microprocessor. All right, now that I've talked you through this, let's watch the video so you can kind of get a sense for what this process is like. Bear with me here, because we have to watch the advertisements. There we go. Skip over that. All right, so starting with sand. The sand is taken up here. It's melted down. It's put into like a big vat furnace, so you have this molten material. It's put into like a hot cylinder. All right, this is going kind of fast, but just so you see, this first step here is called the Czochralski process. So all this molten stuff is put into a cylinder. There'll be a slide on it next, but that's where it forms this thing called an ingot. Now, it showed you this isn't happening in 1 second. The actual process is much slower. Once you have the silicon ingot, keep in mind, this is all one big block. It's one big cylinder of single crystal silicon, where silicon has those atomic bonds that they formed with all the neighboring atoms. Okay, so this is all single crystalline material. Now they come through with a saw. Doesn't actually look like this. The saw looks different in real life, but the basic idea is they are cutting that big cylinder into thin slices there. One step they didn't show you is that they, after cutting it, they polish this to like an atomic flatness. It's atomically flat, and so that's why it's very shiny. It looks like a mirror. All right, now this is the key step, the key set of steps. There's like over 200 steps that are done here. But what this video is showing you is just some snippets of some of those steps. And right now, the first thing that you're going to see is a process called lithography. Lithography is the process that's used to define where you want the source of the transistor, where you want the drain of the transistor, where you want the gate of the transistor to go. Right? All these things are designed on computers, but then those computer designs have to be translated and actually manufactured on this what's called a silicon substrate, these wafers here. Okay, so you're going to see the first step of a lithography process. Lithographic processes are done using an optical technique where you shine light through something called a mask. A mask is transparent in certain areas and it's dark and it's opaque in other areas. So what that means is that you're going to get a pattern. The shadow that's projected down on the surface of the wafer is going to be lit in some regions and dark in other regions. So it's like you could say it's like a picture, if you will, a picture that's formed on the surface of the wafer. Now, the reason why this is moving up and down like this or back and forth is because let's say your mask pattern has the mask for a single microprocessor. A typical wafer will have hundreds of those microprocessors on there. So that pattern will actually have to be repeated at multiple locations. So this is called a step and repeat process. All right. Now it skipped over some very important steps within the lithography process, but we don't have time to go into all the details of that right now. But just recognize that light is used to form certain patterns. And there are some light sensitive materials on the silicon that's placed on the silicon chip, on the silicon wafer. Those light sensitive materials are kind of like film. If any of you have done like photographic film, not digital photography, but like old school film photography, where you take a picture and then you actually develop the film. Okay, the films are actually light sensitive materials, so parts that are exposed to light, their properties change compared to the regions that were not exposed to light. So this allows you to actually like create a pattern of chemistry on the surface of these wafers. And it turns out those patterns of chemistry can be translated later into regions where you will have a source and a drain, or you'll have like an interconnecting metal or not, and so on. So by the first part, if you look at the bottom here, okay, if you look at this green region, this is part of the channel region of a transistor. So there are certain steps that are done here. This video is going super fast, so you really don't see like all the stuff that's happening here. But the first part of the fabrication process is that you form some of these wells, and within those wells you form transistors. So you can kind of think about each one of these blue regions as being a transistor. And then after that, you form the interconnects between the transistors. So for those of you who have like, maybe built a circuit before, either at home or in an electronics lab, you know that you connect resistors and capacitors and transistors together. You connect them together with wires. But on an integrated circuit, the transistors are connected with layers of metal. These metal layers are called interconnect layers. And if you imagine the fact, as we said, like there could be 10 billion transistors on a chip, the metal interconnections between them, how these transistors are connected to each other, can get pretty complex. So connecting one transistor to another is like a whole series of different metal layers, going back and forth, horizontal, vertically. It's just a mess of wires on the chip, basically. They're not actual wires, these are like just very precisely fabricated strips of metal. They're called traces, actually. So multiple metal layers. Okay, so what you saw here was a brief overview of something that takes like more than 200 some steps. Okay, so at this point, we fabricated all the key transistor layers and all the 7 to 10 different metal interconnect layers that are required to make connections between all the transistors. And now, as I mentioned before, you see this, if you look closely here, you'll see these little squares. Each square is actually a transistor. I'm sorry. Each square is a microprocessor that has billions of transistors on it. So the wafer, the entire wafer may contain a trillion or more transistors on it. But the wafer is broken up into a grid, and each section of that grid is enough transistors for a single microprocessor. So the microprocessors are just repeated here. So Intel wants to sell a single microprocessor for a single computer, so they chop up this thing by something called a dicing saw. Again, it doesn't look like this. And then after cutting it, you see that little pick and place thing? It picked up one of those little squares on the grid. That's a single microprocessor. Moves it elsewhere. All right, so now you can look to see that this is actually one of the microprocessors. These little robot things actually have a little vacuum suction thing at the end so that it can hold on to the chip without fingerprints. Now the microprocessor then undergoes a battery of tests. Like again, it didn't show, well, I might show this at the end here, but after it's connected down, that chip has, it has 10 billion transistors on it. So you have to do some kind of testing to make sure that those 10 billion transistors are working together as they should. This is coming in, it's putting this metal cap on it. All right, so does anyone know what that metal cap is used for, or why it's important? Why don't they just put this thing on here?
Can I guess a dust cover?
Dust cover, very good point. Yes, that's one of the functions that it serves. These transistors are so tiny that if you start getting like dust particles in there, they might malfunction. There's another important operation of this metal thing, and that is heat dissipation. 80 billion transistors switching on and off, it turns out it generates a lot of heat. And so we need to a way of dissipating that heat. So this metal thing is often connected to a heat sink, and there's a fan in there that just keeps that chip cool. All right. So these microprocessors are sold in these boxes if you make your own computers, or a computer manufacturer like Dell or Compaq or whatever, they will buy a whole bunch of these and they'll assemble them on motherboards, and that will eventually be part of your computer, your laptop or whatnot. Okay, obviously a lot of steps that are left out here, but you know, it just gives you an overview of the process. So let's continue listening here a little bit. Okay. So that is kind of a brief overview of the sand to silicon process. So any questions here? So I know there's a lot of, you may have questions since it's such a hand wavy or high level overview of it.
Yeah, just one quick question about the silicon ingot that was formed.
Yeah.
So you said that process was a lot longer. Is it, do they have, I guess, I'd imagine they have specific cooling parameters in order to get that into a single crystal, or does it automatically kind of, would it orientate into a single crystal?
Yes, yeah, very good question. We will actually be, I'll have a slide on that. I'll talk about the Czochralski process on the next slide. Good question. Any other questions about the process as a whole before we get into the details of the ingot process? Okay. All right, let's see if there's a question here. Okay. So this is the Czochralski process or the Czochralski method. This is what's used to make a silicon ingot from molten silicon. So let's just start by watching this video. I just think watching the videos gives us a nice picture of what's going on. Of course, we have to watch our Verbo videos first. There we go. Okay, now you can't hear the audio. I'll just walk you through some parts of this video. Okay, so what you're looking at here is a big vat where they make the silicon crystals. All right, so there's a chamber here. There's a heater down here, and then there's a heat shield here because this thing is going to get super hot. Now, what you're looking at the top here is you can see that there are pieces of polysilicon here, but this is not single crystal silicon. All right, so you have your polysilicon up there. Now, what we do here is that we melt it down. It's melted down. High temperatures, becomes a liquid. Okay, over 1,000 degrees. So this is called the silicon melt. The next step is that you start with the seed crystal and you dip it into the melt. Now, this is one of those things about it's like a chicken and egg thing, right? In order to make a crystal, you actually have to start off with the seed crystal. Now, how they got the seed crystal to begin with is it's from a previous run of the Czochralski method. But then you might ask, well, who did it the first time? I don't have a good answer for that. It's like when you make yogurt, if you make yogurt, you always have to start off with a starter culture. Anyway, so the seed crystal is single crystal silicon. Okay, this has a nice crystalline atomic structure that's used as a template to make the rest of it. You dip the seed crystal into the melt, and you notice that it's rotating. And then you start the crystal growth. Notice what's happening here. If we watch this again, you'll notice that this spindle, it's spinning at a very specific rate, and it's also being pulled out at a very specific rate. Those two parameters, actually there's three parameters. One is how fast the spindle is spinning. The second is how quickly it's being pulled out. And the third one, of course, is just the temperature of the melt. So as it's being pulled out, you can see that there's this ingot that's magically appearing here. What's happening is that this molten silicon is cooling. And so it goes from a liquid state to a solid state. So you're pulling out the liquid, but then the liquid rapidly cools, so it becomes a solid, and it comes out in the form of a cylinder. So what happened here is that if you look at what's happening on the atomic scale, the seed crystal is single crystal silicon, and the atoms in this melt, you can just imagine that the atoms are just attaching themselves on to the lattice. They're attaching themselves onto the end, and it's because it's at high temperature, the atoms are organizing themselves into a single crystal form. So that crystal just grows when this is done at the right conditions. Okay, so the ingot is basically pulled out slowly. So there's cooling happening, there's rotation happening. Eventually, all the silicon in the melt is consumed, and you're just left with this tall ingot. made of single crystal silicon. Now, the size of the ingot determines the size of the silicon wafers. I guess I'll just touch on this. Why not? They cut something called an orientation flat. We'll talk about that in a second. And they have to go and slice this thing up. You can read what's happening here. This is a really cool animation. These strings are actually cutting the ingot into thin slices. These little things here are diamond coatings. Diamond is good at cutting things. After you cut, you're going to have rough surfaces. So there's this process called CMP, chemical mechanical polishing, where these wafers are put in these rotating discs, and there's this cap that comes out on top that has etching chemicals on it and also mechanical just movement that is basically grinding the silicon wafers down and polishing them so that you have a very smooth finish. All right, the next step here is that they're dipped into these etchants, and these etchants basically, like, they smooth out the roughness of the silicon. This is the last step here, polishing and cleaning. This is done with something that seems kind of low tech. There's like a polishing pad. This is forming atomically thin, atomically flat layers. They have a slurry. It rotates within that slurry, pushing up against the pad. You end up having like these very nice flat silicon wafers. All right, so this gives you a bit of a sense for what's happening here. So schematically, it's showing the same thing. Oh, hold on. I'm getting advertisements. There we go. So you melt the polysilicon, you introduce the seed crystal, you start pulling the seed crystal out at a specific rate, and you form this thing called an ingot. Now, there's a process called doping, which can be done during the silicon ingot formation. We'll talk a lot about doping in Module 3, but doping allows you to create something called P-type or N-type silicon. And most wafers that are made are doped, typically doped P-type or N-type. Okay, and when you do doping, you have to consider that consider this equation. There's something called the distribution coefficient, K sub D, and this is equal to the desired impurity concentration in the ingot, and then Cl is the dopant concentration in the molten liquid. So you're basically adding your dopants into the molten liquid. If you want to add if you start out with silicon, for example, if you want zero doping, no doping, you just put all silicon, pure silicon in there. If you would like to have P-type doping, then you add a column 3 element. If you want to do N-type doping, you do a column 5 element. Okay, we'll talk more about that later, but you can kind of tune the properties of your semiconductor by adding some dopants or impurities into the lattice. Okay, where are we now in terms of time? I want to make sure we get through this material today. Okay, there's another method for making three-dimensional crystals. So one was this VAT method, the Czochralski method that I showed you. The other layer is called like molecular beam epitaxy. And some people also refer this to another technology which is closely related to this called atomic layer deposition, or ALD. So this type of approach is very different. It's done in a vacuum chamber. And this is just this complex thing you see here. This metal vat is essentially a vacuum chamber. And in those vacuum chambers, they can also precisely flow in certain process gases. So you start off with the wafer at like ultra high vacuum. So there's literally nothing in there. And then you start flowing in, you can start flowing in certain process gases. And then you can also, you can add in what's called like the elements. You can literally add certain elements to it to grow things layer by layer. So in this example, you have these a substrate that's up here. So that's the thing that you start off with that's inside the vacuum chamber. And then you have these different things that you can add to it. You can add a layer of silicon. You can add a layer of aluminum, a layer of gallium, and so on. These are called your sources. They're held in crucibles. There are shutters. And when the shutters are moved away, the silicon atoms can evaporate, for example, or sometimes they use high temperature, they use electric fields to basically take some of these atoms and push them towards the substrate here. A variety of techniques that we're not going to get into, but you can basically add things, create layers of materials at atomic scale. So this is what something might look like. Let's say you see these light and dark lines that you see here. This is 10 nanometers, by the way. So, you know, this here would be literally be 1 angstrom atomic scale. So you can build very, very, very thin layers, 1 angstrom at a time. Okay, atomically thin layers of different materials. So this is these types of systems are used when we want to create something called heterojunctions. Heterojunctions are where you have layers of different materials, and you can, you know, you can do all sorts of cool things by modulating the band gaps by choosing certain materials and thicknesses and things like that. Another term that's often used, they're used to create alloys. I mentioned heterojunctions, but a more general term is like alloys, which is mixtures of materials for tuning electronic properties. And within the scope of epitaxial growth, I mentioned that there's different types of flavors that you can use. One is chemical vapor deposition, or CVD. This is where you have processed gases flowing in. The gas will flow in. There'll be a reaction that happens on the substrate, and you'll start growing a thin layer on the substrate. Vapor phase epitaxy is where you heat up crucible, and some of that silicon atoms, let's say it goes to the vapor phase, and the vapor phase, it deposits themselves on the substrate. With molecular beam epitaxy, you start using electric fields, and the electric fields can be used to remove silicon atoms from here and bring them down into the substrate where they can be added layer by layer. Okay, so it's really cool that we can actually fabricate extremely thin layers of material that are at atomic scale. We can make all sorts of crazy, fun electronic materials this way. Now, if from the video, you might remember the ingot wafer was being cut. One side of it was cut like this. Okay, instead of being a cylinder, so instead of being a complete circle, the wafers are they actually have a cut on one side. And that is just a notation. It's a way to mark the wafer and indicate what type of wafer it is. Depending on where those wafer flats go, this is considered a wafer flat where it's cut like this. The wafer flats indicate what type of material it is, if it's doped p-type or n-type. And it also indicates where the silicon was cut, meaning like along what crystal plane was it cut. So just so everyone has a clear idea on this, just if we draw our crystal plane again like this. This is our model of the lattice structure, and you know we have our atoms here. I'm not going to bother drawing all the atoms because it'll get cluttered really quick. But if we want to have what's called a 100 wafer, we would cut it like this. When we go to cut our ingot, we cut it horizontally like that. And we would get the 100 plane. So a 100 wafer means that the surface of the wafer is has the same atomic distribution as the atomic distribution on the 100 plane here. Okay. You could also have wafers that are along the 111 planes, which means you have to cut kind of like diagonally like this in order to get a 111 wafer. 111 wafers are more expensive. They're less commonly used. 100 wafers are the most common. And these are just some examples of what the wafer flats might look like, depending on what type of, you know, what orientation of semiconductor wafer that you have. Okay. So the next thing you can think about is the diameter of these wafers. How wide are they? Common diameters are 50 millimeters, 76 millimeters, 100. What's happened is over the years, so this gets to one question I want to ask everyone, if you think about it. Over the years, what we've seen is that the diameters for these wafers have increased from 50 millimeters, then they went to 76, then 100, 125, and now we're up to 300 millimeters or more. The wafer sizes have basically been getting larger and larger and larger. This is a good scale because it has a human in there. 200 millimeter wafers in the 90s, 300 millimeters in the 2000s, 450 millimeter wafers starting in 2015, even bigger in the future. They'll literally be the size of an extra large pizza. Question is, why? Why are we seeing this trend? So I want you to think about this for a while and see what you come up with. You don't have to have the right answer, just looking for thought processes. So this chart is showing this trend over the last several decades. Bigger and bigger wafers.
Maybe we've gotten better at making them.
Yep, absolutely. So Clayton said that we've gotten better at making them. Absolutely, that's one of the reasons. Before, we didn't have the reliability of our processes in order to make in order to have reproducible properties throughout the entire. Maybe we were able to make it at 2-inch scale. We were able to make reproducible properties in a 2-inch wafer, but the larger the wafer gets, the more difficult it becomes to make sure the whole thing is very reproducible. You know, meaning that the transistors that are built on this side of the wafer have the same properties as the transistors on the other side of the wafer. The larger it is, the harder it becomes to do that. So that's part of the answer. So Clayton said, like, our manufacturing processes have improved to make things more reliable. Yes, absolutely. But what do you think is the motivation? Why would we want them to make it bigger? Why would we want to make the wafers larger to begin with?
You said they go through like 200 processes. So if you can get more, I guess, micro chips on this thing, then that would, I guess, be more efficient to
Yeah,
manufacture.
exactly. You hit the nail right on the head. Yeah, thank you, Corey. This is exactly it. This is a batch, what's called a batch fabrication process. We're not making transistors one at a time. We're making transistors literally almost trillions at a time. The same 200-step process can be used to make a single transistor or 10 transistors or a trillion transistors. The same 200-some steps. Okay, so why not just make a whole bunch of them at the same time? The more we can manufacture together, the better off the economies of scale are. This is the reason why the cost per transistor has gone down by so much. If you look back in the 1960s, as the wafer sizes have increased, you look at this red line here. The cost for a transistor has gone down incredibly low. Back in the late 1960s, one transistor cost $1. Just think about that for a second. If each transistor cost $1 and our typical cell phone has 10 billion transistors on it, the cell phone would obviously cost $10 billion. Not particularly affordable. But what's happened is that as we've increased the sizes of our wafers, we're able to fabricate more and more transistors on the same wafer. So that brings down the cost of the transistor. And this plot, this is in log scale. It nicely shows that the cost per transistor has actually gone down by a factor of 8 orders of magnitude. Think about that. As engineers, we get very excited about 1 order of magnitude. Hey, you know, like the fuel economy for this is 10 times better. Imagine that if we had 10 times better fuel economy for a car. Or the weight, the battery life is, you know, we say it's 10% better. But what if it was like 1 order of magnitude better? What if it was 10 times better? Now think about 8 orders of magnitude, 10 to the 8th. Is the cost has gone down by a factor of 10 to the 8th. So really, it's quite remarkable what the semiconductor industry has been able to do over the last 35 years and even beyond that now. Okay. Any other questions? Silicon wafer sizes. Okay. We talked about this in class last time, so I won't mention too much about it, just a few highlights. We have remind everyone that we're making transistors smaller and smaller and smaller. That is what Moore's law is. By putting more and more transistors on a chip, we're able to, number one, get more complex computation, and number two, the transistors actually operate faster. So you get 2 big benefits of it: more complex calculation and faster performance. That was a 4-decade trend. These were some numbers that Intel likes to talk about: 4,000 times faster, 5,000 times less energy, 50,000 times cheaper. This was an interesting slide that sort of showed some of the process innovations that needed to be done. So back in 2003, they started using strained silicon, a strained lattice, where they had some impurities in there to make the lattice a little bit different. I'll show you that a little bit about that later. 90 nanometer processes down to 65 nanometers, 45 nanometers. By the way, these numbers are talking about the gate length. The gate length, the length from the source to the drain of the transistor. So by 2007, they were working on 45 nanometer node sizes. By 2009 and 2011, they were down to the 22 nanometer node sizes. Now here, in order to make these generations of transistors work, Intel had to they had to go to a high K metal gate, like a high K dielectric, in order to make sure that the threshold voltages were large enough. So, and then here, we talked about this in class the first time, is that the on-off ratio of current became quite poor with the standard 2-dimensional transistor. And so Intel had to come up with a new architecture called the tri-gate or FinFET transistor, which allowed you to have the better on-off control. Okay, I'm throwing out a lot of numbers here, like a lot of specs that I know may not make all that much sense to you until we talk about the transistor chapter. So I recognize that, don't worry about it. I guess the thing I want you to come off with here is that it's not just a matter of just making the transistors smaller and smaller. There is actually a lot of engineering innovations that have to go along with that in order to make sure that the transistors operate at these smaller scales. Okay, so it's not that a trivial, or it's not just a matter of making them smaller. And then so the R&D pipeline, this is something that was from 5 years ago, but it's reasonably accurate in the sense that back in 2013, they were developing 14 nanometer processes. In 2015 plus. We are at this level right now where some of the state-of-the-art transistors are in the 7 nanometer range. Okay, and there's an interest in pushing forward to the 3 to 5 nanometer region, but those there's still some more innovations that have to be done in order to get to that node size. You just think about how small this is. It's mind-boggling. All right, but there's so much in our world economies and life that depend on us being able to push forward with smaller and smaller transistors so that we can get better compute, lower power compute, and less expensive electronics. All right, so where are we at right now? 6:42, good. I think we can get through some of these key points in the next half an hour. Just close this for now. Oops. All right. Okay, let's talk about crystal defects now. So we talked about what a perfect crystal lattice looks like. This is where every silicon atom is bound nicely to other silicon atoms around it. Okay. And this process just repeats, this. I'm not going to bother drawing this. Just imagine that you just have this sea of silicon atoms. But the reality is that even though our ability to make ingots at atomic scale is very, very good, it still has some defects in it. So we just have to be aware of what types of defects we can have and how those defects impact semiconductor performance. Imperfect manufacturing processes. So there's 4 different types of crystal defects that we can imagine. So let's look at this for a second. So ideally, you'd have something that looks like, Ideally, you'd have something that looks like this. Every silicon atom, example, case in point here, is bonded to 4 silicon atoms around it, and it forms a nice repeating lattice. But in reality, what happens is that there are certain defects that show up from place to place. Now, the defect rate may be fairly low or maybe higher depending on how good the process is. 4 different types of crystal defects. We'll start with number 1. The first one is called a dislocation. So a dislocation occurs at grain boundaries. So if we jump down here, if you remember looking at the diagram for polycrystalline silicon, polycrystalline materials have nice crystal properties in certain regions, but it's kind of a collection of crystalline materials where they're connected together, but they have crystal defects along these boundaries. These boundaries are called grain boundaries. Okay, the types of defects that occur at the interface between 2 crystalline sections of the material are called dislocations. Okay, so you can kind of see here that this is one crystalline material. It has a nice line of silicon atoms here, another line of silicon atoms here. But when this thing bonds, instead of this atom bonding to this atom as it should, it bonds to the one next to it. And so it leaves kind of like this distortion in the lattice, and that's called a dislocation. The second type of impurity is called an interstitial impurity. This is a small impurity atom that fits between the atoms in the lattice. Okay, so imagine that you have, let's say, like a small atom, like I don't know, you can pick any small atom, like like an oxygen, for example, and that is that it's pushed in between the silicon atoms here in the lattice. Okay, so the existence of this impurity actually stretches out the lattice here because it has to make some space for this additional atom here. Okay, and so this changes the shape of the lattice. When you change the shape of the lattice, the electronic properties are going to change. The third type is a vacancy. So this is the opposite of the interstitial impurity. The interstitial impurity is where you had an extra atom that was sort of pushed in there that wasn't forming atomic bonds in there, but it was distorting the lattice, extra atom. And a vacancy is a missing atom. The missing atom will distort the lattice in a different way. It'll actually cause the crystal lattice to collapse a little bit in that region. That will also change the electronic properties just in that area. The last one, last but not least, is a substitutional impurity. Now, this type of impurity is where a dopant atom replaces another atom. So if I were to, let's say, delete this silicon atom, okay, and replace this with, let's say, phosphorus. So phosphorus, we're going to talk about doping a lot in the third module. So I'm not going to get into all the details of this, but when you switch out silicon, which is a column 4 element, with phosphorus, which is a column 5 element, it brings in an additional electron. So this additional electron is, it turns out that it's free to move about the lattice, and it creates an electron in the material, and that creates a more conductive material. That's called doping. That's doping N-type. Okay. So just suffice to say that these substitutional impurities, where you intentionally bring in a different type of atom to replace the silicon atom as part of the lattice, that is a very important part of semiconductors, and it can change the semiconductor properties. Namely, we talk about making a semiconductor P-type or N-type. If you dope with column 3 materials, you can convert it to P-type. If you dope with column 5 materials, you can create an N-type material. All right, let's talk about carbon bonding in 2D versus 3D crystals. Where are we going here? We spent a lot of time talking about 3-dimensional crystals, and that's been the mainstay for the past several decades. But what's become important and interesting in the last 10 years is the idea of 2-dimensional electronics. All right, so we're going to start off by talking about how does bonding look different in 2-dimensional materials versus 3-dimensional materials. So this is what we know already. Okay, column 4 elements form tetrahedral bonds. We talked a lot about silicon, but remember that carbon, which is shown here, carbon is also a carbon is also a column 4 element. So carbon bonds very similar to how silicon does. Okay, each carbon atom forms covalent bonds with 4 neighboring carbon atoms. Okay, remember carbon has 4 electrons in its outer shell. All right, so it bonds exactly the same way silicon does. This is the covalent bond model, the Lewis dot diagram model, and this is the stick model that we write out on paper. And we know that in 3 dimensions, when you have a tetrahedral bond, 4 covalent bonds, they will form this type of tripod-looking structure with a 109.5 degree bond angle between the bonds. So this forms a diamond lattice. In fact, the reason why the diamond lattice is called that is because when carbon does this, it forms a carbon in a crystalline form like this is basically diamond. Right, and just as like a piece of trivia that you might find interesting is that as we've gotten very good at making single crystal silicon with ingots and all sorts of fabrication technologies. It turns out like that we've become very good at making crystalline carbon too, which is basically diamond. So you've probably seen or heard of laboratory grown diamonds that have defect rates that are better than naturally formed diamonds. So that's sort of changed the diamond industry a little bit, I guess. Diamond is actually used for semiconductors too. It has a wide band gap. It has interesting properties that are used in certain types of applications. Okay, so that's 3 dimensions. Now let's talk about 2 dimensions. Instead of tetrahedral bonding, a 2-dimensional electronic material called graphene, it creates something called planar trigonal bonding. Okay, this is what it looks like. A carbon atom bonds to 3 carbon atoms around it instead of 4. All right, now you might be asking, well, how does that work? Because if you only took 3 of these bonds that you see here, then the carbon atom wouldn't have 8 electrons in its outer shell. So how would that work? And it turns out the way that it makes itself happy is that it creates what's called a double bond. It creates a covalent double bond with the carbon atom next to it. Okay, that means that this carbon atom provides 2 electrons, the neighboring carbon atom provides 2 electrons, and they form a covalent bond that looks like this. Okay, so there's actually 2 2 hybrid orbitals that are next to each other, that contain a total of 4 electrons. And so you have 4 electrons here, 2 here, 2 here. So the carbon still has 8 electrons in its outer shell. It is chemically stable. The way that we draw this in a simplified stick model is that we just draw 2 lines here indicating a double bond. So remember, each line represents 2 electrons. So there's 2 electrons here, 2 electrons here, and then you have 2 electrons here, 2 electrons here. Total of 8 electrons, carbon is happy. Okay, now if you notice that we draw this in a slightly different format here, where we have like the 4 bonds, we draw them in a cross formation. Whenever we have this sort of double bond here, we draw the carbons off at an angle to kind of reflect what happens in the actual lattice structure. This is what the actual lattice structure looks like. So you have a carbon atom. A carbon atom forms a double bond with the neighboring carbon atom, and then it forms a single bond with 2 additional carbon atoms. Okay, let's say you repeat that pattern again. This carbon atom also bonds doubly with the carbon atom next to it, and it has 2 single bonds. So if you repeat that pattern over and over and over again, what's very fascinating is that it forms this kind of honeycomb lattice. A honeycomb lattice looks like this. It looks like a bunch of hexagons. Hexagon is a 6-sided polygon. And in that hexagon, you'll see that there's 2 of the sides have double bonds, and all the remaining sides have single bonds. Okay, you just look at this pattern. I don't think it's worth it for me to describe to you what this pattern is. It's best to just look at it and understand for yourself. So this is a stable bonding configuration for carbon. And since it stably bonds in this form, this has become a material that is well known and well used in electronics right now. This is a material called graphene. Let's just have a show of hands. How many of you have heard of this material graphene? Have you heard the word graphene before? Tori, yeah, you've heard of it? Good. Anyone else? Clayton, Gunan? Okay, all of you. That's great. That's great. Yeah, so let me, if you don't know the details of what graphene is, it was discovered recently. By recently, I mean like less than 10 years ago, or slightly more than 10 years ago, but it won the Nobel Prize in 2010. Okay. Graphene is a 2-dimensional lattice of carbon atoms. And it turns out it has some really, really cool electrical properties and mechanical properties. They're bonded in a 2D honeycomb sheet, as I mentioned. It is the thinnest and strongest material known to man right now. The in-plane stiffness is more than diamond. So if you imagine like a single layer of atoms, it turns out that the bonds between that single layer of atoms is extremely strong. And the in-plane stiffness happens to be greater than diamond. Now, the out of plane stiffness is not that strong. You can see that, that's the fascinating thing about it. You can see in this picture here that with graphene, you can actually fold it. You can fold it and bend it. It's not how we usually think about electronic materials. We usually think about electronic materials like being metals, and metals you imagine like bending a wire, and it stays bent, right? We also think about like metals not being transparent. So graphene was such a cool material because it's bendable. These thin sheets that are highly conductive, you can also bend them. If you try to stretch them in plane, very hard to do that because the in-plane stiffness is better than diamond. But the out-of-plane stiffness is very low, so you can bend it. It's really fascinating material, and there's all sorts of interesting applications that have been found, ranging from transistors, gas sensors, and nowadays like flexible electronics is very important. So graphene is being used in some types of flexible electronics. I've heard that it was used in some type of display technologies because it's transparent and flexible. Another cool property of graphene is that when you have two-dimensional materials like this, it turns out that electrons can flow very quickly through that material. There's less interference. Let's just leave it at that. So they can move at speeds 50 to 100 times faster than three-dimensional materials. So they end up having a very high electrical conductivity. Conductivity is a material property that indicates how easily electrons or holes move through the material. A cool story behind graphene is how it was isolated. They used Scotch tape, believe it or not. The process that Guillaume and Novoselov used to create graphene, they didn't do any kind of like layer by layer synthesis or anything like that. They took graphite, which is basically like the material on the tip of a lead pencil. Well, it's not lead, right? It's lead pencils are a thing of before, but like regular pencils, they're the black stuff is made of graphite, and turns out graphite is just multiple layers of graphene. So they took a piece of Scotch tape and they just pulled the Scotch tape off, and you end up getting a layer of graphene on the Scotch tape, which is quite amazing. This is called the fancy name is mechanical exfoliation. The colloquial name is the Scotch tape method. Now, once you have graphene, a sheet of a single monolayer of carbon atoms, you can actually, well, not by hand, but these types of sheets can be manipulated into carbon nanotubes. They can also be organized into like spheres, which are, so the tubes are called carbon nanotubes, and if you make a ball out of it, a sphere, that is called a fullerene. Okay, so these are two-dimensional electronic materials. Carbon nanotubes, we just look at this material. This is sometimes called a one-dimensional material because the electrons can only flow in one direction through it. Okay, if you look at graphene, it's a sheet, right? The electrons can move any direction in plane of that sheet. But in a nanotube, the electrons can only move in a single direction through it. Okay, I'm just going to touch on this, not too much details you need to remember here, but a carbon nanotube is basically a tube that resembles a rolled up sheet of carbon atoms. Okay, and there's, depending on how you hypothetically cut the sheet, depending on the angles of the carbon atoms, you can have what's called different chiralities. There's a zigzag, an armchair, chiral here. So they have slightly different orientations of the carbon atoms along the boundary of the tube. Okay, the way that these carbon nanotubes are made, by the way, you don't start off with a sheet and then try to roll it up at the atomic scale. No, that doesn't work. They are grown using a chemical vapor deposition technique, which which uses hydrocarbon gases, and those hydrocarbon gases are slowly put on the substrate using a process called CVD, and they literally grow up from the surface like this. So it forms like these little hairs, and each one of these hairs are either a single layer thick, which is called like a single wall nanotubes, SWNT, or there are multiple layers of tubes that are concentric to each other, and those are called multi-wall nanotubes. So concentric means like you have one tube here, you have another tube around it, other tube around it, like that. So both single wall and multi-wall have their own applications. Okay, so they've shown interesting things like this. You can read some of these papers if you're more interested in finding out more about these. Now, one of the things, just by looking at the structure, I just want to point out for carbon nanotubes, one of the reasons where people were very excited about it and still are, is that it forms forests. Forests, like literally like it looks like grass here in some of these pictures, but these are 1 micron wide and they're fairly tall. The surface area to volume ratio in these structures is incredibly high, because you look at all the surface area that just one little post has, and that has a lot of surface area. When you have a series of posts like this or something like grass, there's much more surface area in something like this compared to just a flat surface of graphene. So it turns out that because of that high surface area to volume ratio, carbon nanotubes are really good at sensing things in the environment. They're used as gas sensors. They're used even for like solar energy. There's a lot of research going on in the use of carbon nanotubes for converting light to electricity and so on. A lot of interesting applications for carbon nanotubes. So when we talk about how we make these 2D materials, it's a little bit different than the traditional lithographic approaches. It's obviously different from the Czochralski process that I mentioned to you earlier. So I just want to touch on a few of these things, and then we'll wrap up today's class. So the first method is what I mentioned earlier, is the Scotch tape method, mechanical exfoliation. This is where you take a material that has, like graphite, that has layers, basically layers of carbon sheets on it, layers of graphene, and you just have to pull one layer off with the Scotch tape method. So this, what I'm circling here with my hand here, that is the tape. And the idea is that on that tape, you're just going to get one layer of atoms on there. So you'll get your graphene. Now, this method in practice, it has a low yield of monolayers, which means that a lot of times the Scotch tape won't just pull off a single layer of atoms. It'll pull off multiple layers. So multiple sheets of graphene it'll pull off. And when that happens, you're going to have properties that are similar to graphite. So that's not as interesting. So getting a yield of a single layer of carbon atoms is the tricky thing with mechanical exfoliation. But the good news is that when you are able to get a monolayer, they have relatively low defect rates, and you'll have relatively large flakes, like large meaning like hundreds of microns wide. So this type of thing is good for lab research. Liquid exfoliation, but good for lab research meaning it's not so good for industrial scale up, unless you can imagine having a factory full of thousands of workers who are using Scotch tape to pull off graphene. Obviously that doesn't work. So another method is called liquid exfoliation. And this is where you'd perform sonication in an organic solvent. Organic solvents would be like, an example of a solvent might be something like alcohol, right? Some kind of liquid. So you put your material in there, and sonicating means you, like this is the same kind of stuff that's done for jewelry cleaners. There's a vibrating ultrasonic element in there that creates vibrations within the liquid. So those vibrations create tensile stresses, tensile forces, and that forces these layers apart. So imagine if you start off with a material like this that has multiple layers of carbon sheets like this. Now the carbon sheets are kind of stuck together with something called van der Waals forces. So if you shake it enough, those layers can come apart. All right, so within the sonication, it can force those layers apart. This has low yield as of now because it's a chemical process and they're hard to recover. But if we can get it to work, then it becomes more scalable than the mechanical exfoliation. So this is better suited for industrial processes. Because you're doing sonication, your flakes are kind of smaller than the larger flakes that you'd get with mechanical exfoliation. All right, and the last one, like these two methods are called top-down techniques. And this last set of methods is called bottom-up synthesis. Now, this is similar to stuff we talked about before when we were talking about layer by layer atomic deposition. So CVD, molecular beam epitaxy, these are ways where you can basically deposit carbon atoms or other materials like one atomic layer at a time. So this allows you to form very, very well-controlled layers. Okay, so this is scalable, it's well-controlled, but it requires these more expensive instruments. Then there's other solution-based chemical synthesis methods as well, which we won't go into right now. If this is an area that you're interested in for your course project, I'd recommend that you can start by reading this review paper that was published in 2019. Okay, so we talked a little bit about how some of the two-dimensional materials are fabricated. We also talked about how three-dimensional materials are fabricated. Some of the key points about 2D materials, I just want to put this out there, that 2D materials are multiple layers of covalently bonded atoms that are held together by van der Waals forces. So think about it as a bunch of sheets that are basically stacked on each other, and those sheets are held together by van der Waals forces. The sheets are incredibly stiff in one direction, so if you try to pull sheets in this direction, if you can look at my video, in this direction, it's very hard to rip the sheet. On the other hand, the outer plane stiffness is very weak, so you can fold the sheet very easily. High surface area to volume ratio in 2D materials and 1D materials. They're highest in 1D materials, obviously. So this makes them great sensing devices. Because sensors, good sensors have high surface area to volume ratio. 2D materials have in-plane periodicity and no out-of-plane periodicity, meaning there's a crystal structure in the XY direction, but there's no crystal structure in the Z direction. So this gives it like very interesting band structures. We'll talk about band structures in the next module. And these can lead to high mobility. Mobility we talk about in the third module, but basically mobility is how fast do electrons move through the material. When electrons move very fast through a material, that means the material is very conductive. If electrons bump into things and they move slowly through the material, that's a lower conductivity material. Other things too, like something called dielectric screening. There's something called confinement, quantum confinements. These are all details that, it's beyond the scope of this class, but it just wants you to know that these 2D materials are very interesting because you can control some of their properties, for example, optical absorption and emission properties. Okay. The last thing I want to mention here is that 2D materials have become more commercially available. When I started teaching this class, you would not find this, but nowadays you can just find a bunch of vendors that sell not just graphene, but all sorts of two-dimensional materials. And these materials are being used quite frequently by researchers, electronics researchers materials, to understand their properties and see, like, is there a material that could replace silicon in the future when we start making our transistors into single layer transistors? All right, summary and take-home points for Module 1. I'm glad we're able to finish this today. So we talked about crystalline, amorphous, and polycrystalline materials. Okay, there's three types. Crystallines have a three-dimensional repeating structure. Amorphous materials are random arrangements of atoms, and polycrystalline materials are crystalline materials pieces of crystalline materials attached, connected by grain boundaries. We talked about elemental versus compound semiconductors. So elemental would be something like silicon, all like a column 4 element, and everything's just a column 4 element. Compound semiconductors is when you combine elements from column 3 with elements from column 5. So gallium arsenide, indium phosphide. This is where you take 50-50 mixes of 2 types of materials. And compound semiconductors have interesting properties. They also form the same type of diamond lattice. We talked about the basic unit cells in semiconductors, basically the diamond lattice and the zinc blende lattice. Miller indices, I showed you some examples of how to calculate the Miller indices. You'll have some of that in your homeworks. Today, we talked about different types of crystal defects, 4 different types. We talked about how the atomic structure looks different in 3-dimensional versus 2-dimensional crystals. And we touched a little bit on the 1-dimensional materials like carbon nanotubes. And then overall, like throughout this whole module, we've talked about different types of manufacturing methods. And I hope that you gain an appreciation for these manufacturing methods because they are key to the electronics industry that we have today. You know, very, very important. You know, we can envision 3-dimensional crystals, 2-dimensional crystals all day long, but if we're not able to manufacture them, we're not able to take advantage of all of our knowledge. And really what's happened over the last 6 decades with Moore's law and everything is that it really was a story of manufacturing technology. Transistors getting smaller and smaller, us being able to make them very reproducibly. And so relating this to the rest of the class, we have the ability to make electronic materials with repeatable atomic structures. And repeatable atomic structures relates to repeatable electronic properties. So in the next module, starting on Wednesday, we're going to talk about how the atomic structure of a material relates to the electronic properties of the material. So we're going to talk about things like the Schrodinger wave equation. We're going to talk about band structures, band gaps. We're going to start talking about carriers, electrons and holes. And electronic configuration. So all this stuff that relates atomic structure to electronic properties. Okay, so we'll end here today. We went 3 minutes over. Thank you for your patience here. I will be posting the homeworks in just a couple hours here. So do the homeworks, practice with them, and then the quiz, I was originally planning on making it due on Wednesday, but I want to make sure you have enough time to do it. So the quiz will be due before class next Monday. So look out for that. And other than that, I'll see you in class on Wednesday. Are there any questions today before we end? Clayton, did you have a question?
No.
Okay. Ganan, did you have a question? You have your hand up.
Oh, oops. Sorry. No, I'm
From
good. Have a
before?
great evening.
Okay, good. Anyone else? Okay. All right, good. Then let's, I will stop the recording here and we'll see you on Wednesday.
Thank you.
Thank you.